can prepare a part that same as this image processing session topic. So I guess you will have to bear with me for that. What we're going to talk about is data mining, especially literature mining. And what we're trying to do is we're trying to do full text literature mining and discover protein interactions, so that this will be used as validation for biomarker discovery. The background of this work is what we are looking for. The biologist is searching for the gene expression and protein interactions for drug design, biomarkers, and disease analysis. But there have been a huge volume of research work published in the past. And this including data set, experimental data sets, and also databases that is very difficult for them to keep track of them and find out implicit relationships among those information mentioned in the published articles. And because of that, tools has been developed mostly in identification and extraction of those associations, and also generate hypotheses. What are the possible valid protein interactions among those previous published data? And the whole work I'm going to present is based on a student of mine who had just finished his master's degree. And in his endeavor, we are facing several challenges, particularly in this biological and medicine applications. Authors are not following those standard naming conventions, and that causes many confusions in the terms and create their own terms. So it is makes things discovery a little bit complicated about that. And also the evaluation of discovery is one of the major challenges in this work. The reason is that we do not have a reference. There is no such existing testing data set that is available anywhere. And so what we have to do is to try to locate a database of known protein interactions, and then after we performing literature mining, we'll compare our discovery against those known database and see how far, what's the accuracy of our discovery, whether we have found what we're looking for. And another challenge we are facing is basically because the number of discovered interactions could be too large, too great to validate. Obviously, the whole purpose of this study is to limit the number of hypotheses to the medical side, so that it can be validated in the lab through those cell analysis that I'm not familiar with. But obviously, this is a very expensive procedure and also time-consuming and laboring. We try to limit the number of discovered interactions based on their significance. And access in the past to those published articles mostly limited to the abstract only. And most recently, there are several online databases that provide free article access, including PubMed Central that is supported by NIH, and also others, including in our study is DOAJ is directed access to articles. And the objective of this study is to generate hypothesis of biomarkers by discovering protein interaction from food text articles. And we try to reliable sources and for the secondary relationship and supporting data. And that is one advantage between the full text article and abstract. Abstract usually is more concise way and highlights only a few key findings. But within the description and experiment analysis, including the full text article, we could find additional information between those proteins that was not part of the goal of the study. And also the bibliographical is one area of the research. And also our objective is generate a set of unknown association manageable for biological validation. And this slide shows basically what we are getting by the end of the study. Hopefully we will have a collection of association rules that is evaluated based on the support and confidence, which is a very classical matrices for association rule discovery. And this shows some of those explicit associations, which is protein interactions that already mentioned in the article. Okay, that means there are already studies based on the previous studies that discovered, or at least observed, such interaction happening between those proteins. And this is provide us a base to derive those implicit, or what we also call is novel association, interactions. And finally, we provide a graphical interface. This is not a way to discover additional information, but it provides an interactive way for those biologists to intuitively look at possible connection or interactions between not a pair, but a set of proteins. And that's hopefully the outcome of our study. And this slide just outlines the procedure of this part. The overall view of the project will include both text mining and image mining. But in this, in our current stage, we are focused most on the text mining, and image mining is undergoing. In the text mining, we have several steps. Initially, we query online database and retrieve related articles based on our interest. There will be the terms that, for example, protein names and cancer names that our doctors are interested about. And then after we retrieve the articles, we'll parse it and also tag those protein names and some functional words that it indicates possible interaction. There could be many kinds of interactions, and I'll briefly give you an example of those. And next step is to see whether we are looking at protein names or just some English words, which have in all the articles. And we see some difficulty in that abbreviation of those protein names might happen to be the same as a regular English word. So that way we have basically two ways of validating. One is based on the protein dictionary, which is publicly available. You can pretty much download anytime, and it's updated regularly. And also we have a local lexicon dictionary that is come with the Unix system, includes almost all the English words that are used every day. So we compare with those and identify our protein names that that exist in our articles. Extract those explicit protein names, protein interactions give us a base to find the novel ones, which is pretty straightforward. And all we have to do is to find those predefined protein names and those interaction verbs. And once we have two protein names within one sentence that is associated with functional verb, then it is we are pretty sure that's one of those explicit interactions, and that will be our finding for the for this step. And the last step is, which is the most important part of this study, is to identify those novel ones. As I said, we have we need to balance two criteria. One is to identify, hopefully, all of those implicit interactions. But on the other hand, we do not want to get too much. We do not want to have too many interactions that already not able to be validated in the lab. And what I'm showing here is a web interface. It looks very simple, just provide two user input and a button to search databases. But underneath of it, it provides several functions that is not usually seen in those regular search engines, for example, Google or Yahoo. First, it will connect to those literature databases in the background, and also it will convert those user input and keywords into the format that is accessible by those literature databases. And in fact, this can be extended to many other databases, and we can provide different kind of combination, logical combination of keywords through this input. At this moment, we have only two databases used because that's freely available to everyone, and not just the subscribed. So you do not have to subscribe to those databases. And they do have different mechanism of retrieving, and they do have a different way of presenting their results. So what we are dealing with is we take user input and put it in a uniform way that fits into those database engines, and then after we retrieve, we will have to look for possible redundant articles that could be present in both databases, and then we will stream them off. And the rest will be converted into the text format in XML format for processing. And this just will give us an illustration about what is retrieved. And the articles are actually saved into in our hard disk. But we have a way to save the retrieved article, the name, article name, user name, and also the publication days and so on, so that it's kind of like to the record. And identification of the protein names, because they are a little bit complicated in that way that they do not form our standard way. So we have several strategies to extract those names and the words. One of them is we use a part of script tagging that comes with the Karur language. It's a package which is pretty much all you have to do is to know how to program and what functionality it provides. We basically defined 4 tags. One is a noun, and the other is a plural noun, and also adjectives and verbs, which is the base present form. And strategy 2 is identified by the word morphology, and because we had to use some heuristics here. And we often see use the length of the characters, and we often see those hyphens that we can strip them off. And in the dictionary of the protein names, we have used a very updated data online database called Uniprox database, and we used all the names in there and trying to match in our algorithm. And the elimination by comparison will common nouns identified by having a match against our English dictionary, so that it will be removed if there are some obvious words with refugees not in the protein database. Extract the explicit protein interaction is very straightforward. And I'm going to give you some example about the functional verbs that indicate interactions. So that includes clear, regulate, etc. So those are the keywords. Those are the functional verbs we're looking at. And if they appear in a sentence, the units for those associations are based on sentences, not on article, not on but on sentences. So that's the smallest unit we are looking at. If we have two protein names appear within the same paragraph, but there's no direct indication they are related in any way, we pretty much just ignore. So sentence is our smallest unit. After explicit interaction, we will have pretty much a number of protein names and a number of pair of protein names. At this moment, we only focus on pair of protein names. That's binary interaction. And in the binary interaction, we count the co-occurrence of those protein names and across all articles. And that will be the support of the co-occurrence of two protein names. And also we count the occurrence, the frequency of those individual protein names, and that will be the support for the individual protein. And the hypothesis generation, our hypothesis is represented as kind of associated rule, which consists of two parts. And in here it is X to Y. There's no causality indicated implied in there, but it only means that X and Y possible has interaction. Actually, it can be either X could be here to Y, or Y adhere to X. It does not matter that the order does not matter much in our study. And the metrics used are support and confidence. I just explained a little bit. Our question here is to how to find the optimal threshold so that we will be able to get the minimum number of hypotheses that has the highest likelihood of being valid and interesting and important interaction that could be used as a biomarker for certain cancer. So we need to balance the number and the significance. A priori algorithm is the way we find, we use to find association, and here we borrow it so that we can identify those interactions in our article. It's animation and several times. Okay, this shows what we have extracted initially from the article. Basically, all these names, norms of protein names, they have different IDs, transaction IDs, and after counting through all the sentences in our articles, we will have the support, the frequency of these terms. And then on this one, it shows the frequency of the co-occurrence of pair of protein names. So basically, that will serve as our base for the explicit association notification. And lastly, in the association rule, you need to select this threshold for the association generation. And that gives us basically a list of associations and their support and confidence. In our experiment, since we're dealing with a large number of articles from two literature databases, we're using different kinds of query terms. We will purposely choose some very general terms, which is very general. You can search. If you use Google Doc or Google search, you will be able to find tens of thousands of articles. There's no problem. But here in our, we choose this one to see how many articles were choose. And also we use multi-word general terms, say human protein. And more specifically, we have this HERBB2 as a protein name and breast cancer as a disease name, so that we will be able to see whether you can find those studies on the breast cancer that is somehow related to HERBB2 protein. And more specific, we have a cellular pathway terms, IO2 and signaling. Okay, those are another case for the specific terms, searching terms. And the database we use, as I said, is UAJ and Common Central. Both are